Welcome everybody this morning. I'm going to talk about heteronuclear decoupling here. I will talk about the fundamental problems of heteronuclear decoupling and how you solve it historically and what are the tools that are up to date nowadays. So what's the motivation? Why are we interested in heteronuclear decoupling? When we look at, for example, the carbon 1D, we directly see why we would like to have heteronuclear decoupling. It's simply that the spectrum here of 2 protonal, for example, we have lots of information. We have the coupling, we can get which kind of spin system we have. We have here CH2 system, CH, CH2, and CH3 spin system, for example. But the lines are broadened by the many heteronuclear couplings that each spin experiences. And when we decouple, it's the same molecule shown down here, a decoupled spectrum, then it's much easier to interpret in terms of chemical shifts, and the signal to noise is enhanced dramatically. So what are the problems that we have to deal with? So first of all, what's the principle of spin decoupling? We have 2 spins, a spin I that is coupled to another spin S, and now we have this splitting and we want to remove it. What we do simply is we irradiate constantly on spin 2. By that, the spin states, alpha and the beta state, change continuously, and because of that, the multiplet will collapse to a single line. So when we now look at the pulse sequence, for example, a spin echo, then we always experience 4 cases. And let's look at the spins I and S. The first case would be that we apply nothing, no pulse. In this case, J-coupling chemical shifts on the spin I and spin S, they all evolve. That's the normal case when you acquire the non-decoupled 1D. However, there are 3 other cases when we apply either just a central 180-degree pulse on the I spin or on the S spin or on both spins. And in the last case, again, coupling is active, while the 2 central cases, there we do decouple. And it's obvious which case we would like to have. If we take here the third case, we are interested in recording the I spin and we decouple the S spin, then we get what we want. So essentially, we would like to have such a decoupled spin echo sequence throughout the acquisition. And that means when we look here at our FID, how it's decaying, and we look at a small detail, then we see our FID consists of several defined discrete data points separated by the dwell time. And now between each of these data points, we would like to apply a 180-degree pulse, and then we have heteronuclear decoupling. But of course, there are problems. The first problem is the duty cycle. We cannot apply infinite amounts of RF energy into our probe pad. So when we look at 600 megahertz, for example, then we have typical proton dwell times of 60 to 80 microseconds. On the other hand, if we acquire a carbon 1D, we have, let's say, 30 to 40 microseconds dwell time. On the other hand, the manufacturers tell us that there's a maximum amount of RF energy that we are allowed to put in the system before the probe head breaks. And so for carbon 13, this is about, well, 4,200 hertz, plus minus, depends strongly on the probe head used. But for most conventional proton inverse probe heads, we find that a decoupling of carbon, we are limited to about 60 microseconds. That's the pulse length for longer periods in this. And so a 180-degree pulse would be around 120 microseconds. And we see this does not comply with the dwell times we have, and also proton decoupling, there we have about 70 microseconds for heteronuclear decoupling available, and that is too long compared to the dwell times we have. we cannot apply a 180-degree pulse between two data points that we acquire. So inevitably, we will not be perfect in our decoupling efforts. So we have 180-degree pulses. We violate the upper limit of the 2T cycle automatically. And as a consequence, we will experience sidebands. And also we have to limit our acquisition, because even allowing sidebands, we are at the limit what the probe head can take. So typically spectrometer manufacturers tell us that the acquisition time should be limited to about 200 milliseconds when we use high power heteronuclear decoupling. But what are these sidebands? Ideally, we would not like to have any coupling evolving, which would mean that if we acquire an FID and we neglect relaxation, then we would have here a constant line. I mean, assuming that we're on resonant, we would have a constant line, no coupling evolution would take place. However, in reality, because the pulses are too long, we will have some evolution here of coupling. But then 180-degree pulse is in effect, and then we return, we kind of refocus and get back, and so on and so forth. And when we do a Fourier transform of such a signal, well, we get a pretty well decoupled spectrum, just the line width is a bit broad. We are actually lucky that we get this nice central signal, but you see the signal to the left is periodic, and therefore we end up with some spurious signal where the distance to the central signal here, to the decoupled signal, we see here a small peak. It's like a C13 satellite, for example, in the proton spectrum. And this peak here corresponds to these sidebands. And of course, if you have a modulation that's more complicated, we experience more than one sideband. And be aware that the phase is not necessarily the same as the central signal. So actually the strongest peaks, the strongest sidebands you usually see in periodic sequences are at 1 over TP, TP being the periodicity time, and then this 1 over 2 TP, and they're called the harmonics and the subharmonics. And then many more peaks might appear also from imperfections of the pulse that we use. So we are lucky in some way, because coupling evolution is quite slow, at least in liquid state NMR. So we have couplings here, for example, of 145 Hertz, a typical value for a one-bond carbon-proton coupling. Then if we have here a 180-degree pulse of just 100 microsecond duration, then during this, the evolution reduces our signal to 99.89%, which is almost 100%. And correspondingly, we experience very little sidebands, 0.11%. That is very little. So for 145 Hertz coupling and 100 microsecond, 180-degree pulse length, the sidebands are negligible, just 0.11%. If the pulse is 300 microsecond long, then we already see sidebands on the order of 1%. A 1 millisecond long pulse really then enhances the sidebands up to 11.2%, and a 3 millisecond long pulse will be essentially intolerable, because the integral over all sidebands will be about 80%, and that gives significant problems. Then, then you would not talk about decoupling anymore. On the other hand, if we have smaller couplings, like long-range couplings that we want to decouple only, like couplings, let's say, on the order of 5 Hertz, then it's shown here for 1 millisecond pulse, we do not get 11% of the signal in the sidebands, but we would only get 0.02%. So the smaller the coupling we have to decouple, the easier it is. And if we have a 260 Hertz coupling, for example, in triple bonds, then already 1 millisecond leads to more than 30% of sidebands, and that I think is not really tolerable. Just to show you an example, what you will see quite often in this talk will be this sideband picture here. And this is essentially, you have the central signal, and we look here at the foot, at the right-hand foot of the signal. It should be symmetric, so on the left-hand side, you should see a very similar picture. And here in a realistic and acquired example, then you see here these sidebands occurring on the order of 1, 2, 3%. And when you look in a spectrum, in a 2D spectrum, then you can typically see these sidebands here along the diagonal, parallel to the diagonal. And of course, if you're only interested in the central signal, which is still a factor of 50 larger, then you do not bother. But for example, if you want to acquire a nosy spectrum and you want to decouple a heteronuclear coupling, then these sideband signals here might be even larger than your nosy crosspeak. And then it certainly matters. But there is another problem. And I was talking about applying a simple 180-degree pulse, a short 180-degree pulse. But because we are limited with the RF amplitude, the RF energy that we are able to put in, we also have a strong offset dependence of the pulse. And so what I showed here on the left lower side is the transfer efficiency of Iz to minus Iz of a hard pulse. And when we apply it with a nominal field of 15 kilohertz, we have good inversion on resonant. But when we get 10 kilohertz off, we have an efficiency of less than 80%. And that in a decoupling sequence would not be tolerable as well. Everything I showed you so far was kind of the on-resonant case. But in a real case, we have a quite large spectral width to cover, especially if we want to decouple nuclei like carbon, or when we think of fluorine, then it's even worse. So for this, there are supercycles developed, composite pulses to deal with it, and we will get into this now a bit. So let's look what's the pioneering work, what has been done historically. There are these 4 persons that are quite central in the development of the early ways. And the first thing was here with Anderson and Freeman, was a work of double resonance, they called it. Well, you decouple, and what you do is you simply use CW irradiation on the second nucleus all the time. And here's shown an offset dependence of CW irradiation. So you have a split signal, you have the multiplet, the alpha and beta state, for example, of a multiplet. And then on resonant, where you irradiate on the hetero spin, on the S spin, the splitting of the I spin is shown. On resonant, you really achieve decoupling. The multiplet collapses to a single line. And that was kind of to show, yes, it is possible to do heteronuclear decoupling. So quite an achievement, 1962. And then it was Richard Ernst, actually, who introduced the spin noise decoupling, which is a quite interesting idea. So you create some kind of noise, non-coherent noise, and then you decouple. And indeed, here you see the noise power. And when you cross a certain threshold, then suddenly you decouple your signal. And that with a higher efficiency than you would have done with just a CW irradiation. You even have a small bandwidth to cover, and yeah. And it was only in 1979 when Freeman and Malcolm Levitt looked into something that would be acquire, put in 180-degree pulse, acquire 180 degrees, acquire, etc. Only then this idea that I just showed you has been developed and first taken into place. These are the very first results. And back then it was really the case that with the Q factor in the probe heads and with the spectral width on the, here you see it's 1000 Hertz in this spectrum shown, that the dwell time is so long that you really could do this 180-degree approach. And you see nice decoupling of the signal, just as you would like to have it. Just a bit later, Malcolm Levitt developed the idea that Ray Freeman actually named the composite pulse. I don't know if you're familiar with these composite pulses. The very first composite pulse is 90 degree X, 180 Y, 90 degree X. I think it's easiest to see like the B1 inhomogeneity that is being compensated, you know, when you transfer magnetization from Z to X, for example, then you start with, let's say, 5 spins that have different positions in an NMR tube. And the NMR tube does not feel everywhere the same B1 field. In the center, it's different from somewhere at the edges of your sample. So something in the center, instead of a 90 degree pulse, might experience 110. Then there will be some area where you experience a real 90 degree pulse, and then some area where you only experience a 70 degree pulse. So kind of, if I show this, you can start, and then my fingers indicate these 5 different possibilities in this case of different B1 field strengths. They go out of this, meaning my thumb is slowest and the small finger is fastest. So we went like this, and now you apply a 180 degree pulse. Turn around, and then when you continue with the 90 degrees in this direction, then of course this is the slowest and this is still the fastest. Then they will reconvene and refocus. And this idea is really a great achievement. Today, 1.2 gigahertz spectroscopy would not be possible without these composite pulses. And we use them every day. This was the beginning in 1979. Yeah, just the bandwidth. More and more composite pulses were developed like this 90 to 40, 90, which had slightly better performance. So this is the original 90, 180, 90, and this is the 90, 240, 90. You see it works better, although you do not see it from the pulse directly. And then Malcolm Levitt also developed this supercycle schemes. And the first supercycle scheme, this R bar, meaning you have a base sequence R, which consists of this 90 degree X, 240 Y, 90 degree X. And this you apply with the phase X here for the first pulse, then again with the phase X, and then you apply it with minus X, minus Y, minus X as the pulse phases and repeated. With this supercycle, indeed, you achieve some cancellations of sidebands and you get a much further improved decoupling scheme. And you see this also here in the bandwidth. Back then they compared with a noise decoupling. And you see here, you get wider with this decoupling scheme. So this MLEF4 decoupling scheme was the best at the time. And then, of course, you can enhance these supercycles. You can further expand on it because this 4 cycle, you can read R bar, but also R bar, and so on. And doing it this way, you get even further cancellation of artifacts. And I think I even saw an MLF 128 sequence once. But it's clear you can do this endlessly. But the real big improvement, I think you see up to 16 different phases. And well, then only tiny little improvements are seen later on. And with this pulse sequence, it was the first time worth to define a figure of merit. And this figure of merit Xi here, that would be the bandwidth that you can decouple divided by the B1 field strength that you apply. You know, the shorter your pulse is, which means the higher the RF amplitude is, the higher the B1 field is, the wider is the spectral width that you can address. So the actual bandwidth scales linearly with the B1 field you apply for the decoupling. If you apply it with a 5 kilohertz RF amplitude, in this case 1.5, you get 7.5 kilohertz that you decouple. If you apply it with an RF amplitude of 10 kilohertz, then you get double, you get 15 kilohertz decoupling. And an RF amplitude of 10 kilohertz corresponds to a 90-degree pulse of 25 microseconds. So with this factor 1.5 back then, you could imagine, like I mentioned, today's spectrometer, you have about 4 kilohertz allowed decoupling power level. So with this pulse sequence, you're able to decouple about 6 kilohertz. And 6 kilohertz on proton, that would be exactly 10 ppm. So proton decoupling was already possible. But carbon, well, we're talking about, let's say, 200 ppm on a 600 megahertz spectrometer. That's about 30 kilohertz. So on carbon, we could only decouple a very small fraction of the signals we're interested in. So more composite pulses were developed. Here, an example is 90-degree X, 180 minus X, and 270-degree X pulse. And this formed the basis here for the so-called waltz decoupling that you also may know. And this is expanded here in the MLF4 supercycle, but waltz 8 here then combines the 3 and the 1 to 4, and then the 1 is shifted to the end, and then you get the sequence element here and apply it in MLF4 type, and the waltz 16 has a similar procedure out of these two. And well, with this you get a Xi of 1.8, which is already an improvement. Then there was GAR, globally optimized alternating phase rectangular pulses, GAR. And that was the first computer optimized composite pulse. And in this case, you see that the Xi improved dramatically. And so that was the first decoupling sequences that really fulfilled the needs that you had also for carbon decoupling, a factor 4.8. So with 4 kilohertz RF amplitude that we are allowed, you're able to decouple about 20 kilohertz. And that's already significant. Even on a 600 megahertz spectrometer, we're talking about 130 ppm. And so it's no wonder that this pulse sequence is still in use today, quite a lot of times. But there are better sequences available today. So then Tycho and Pines and Guggenheimer came up with some exotic phase cycles where you do not just take positive and negative pulses, but where you have 0, 120, 60, 120 degrees, and you add a phase that is constantly increased. You add up a kind of a frequency shift with this, and they seem to work better than conventional sequences or supercycles. And then Fujiwara and Nagayama came up also with composite pulses that are a bit different from the others. So exotic composite pulses, Tony called them. And they have not just a 180-degree pulse, but it appears at a frequency that is 1.55 times some value here shifted. So you use now pulses, for example, here 3 pulse elements that irradiate at 3 different frequencies. And that's kind of the first time that you introduce even something that we call today shape pulses within the composite pulses. And with this, so then you take these frequency shifted pulses, you take the new phase cycles, and then expand this phase cycle even further in this MLF4, for example, phase cycle. And that gives you quite an enhancement. So you were able to get a Xi of 6.2. And well, I don't want to show this. And then further inversion pulses were developed And the bandwidth increased dramatically to 9.2 and up to 13.4 for this Xi. And well, you see here 4 examples. This is the GARP, and then the so-called MPF5, MPF7, MPF9. And when you look at the Xis that we measured, then from 4.8 you go to 6.7 and even up to 12.3. And this is quite remarkable. This is really a very strong improvement, and for 600 megahertz, I think this leads to nice spectra. But still, this factor 12.3 means that we have to apply quite some radio frequency to the sample. Now, what then came up in the 90s were shaped pulses. And there were a lot of things here. The Gauss cascades were the first ones derived by Lyndon Emsley and Jeffrey Bodenhausen. And you see they were nice selective pulses. And of course, you can also use them in heteronuclear decoupling. And that's something, for example, here in the Glaser-Griesinger group was performed like multiple selective decoupling, which means in a protein, for example, you just look for the carbonyls themselves and the whatever aliphatic region and only irradiate on those. And then you can save RF energy with this decoupling. And this is shown here. It's experimental data. So here you have the coupling active. And then with different offsets, you see at some point you decouple for a selected region. And you can even have multiple selected regions, like here, this area, and decouple this area, but in between you don't. So the selective decoupling came up. Okay, here's a special shape pulse. Well, it had a Xi of 6.2, Susan decoupling. I don't see it used anywhere, but this was also a nice development at the time. And then Robin Bandel actually started out with adiabatic pulses. So this is a second tangens hyperbolicus adiabatic pulse. So you see here the blue line gives the amplitude and the frequency is given by this tangens hyperbolicus shape. That's the frequency sweep that is applied. And well, he got a Xi of 10.9, which is quite remarkable. And a few months later, there came a decoupling scheme up that we still use today quite a bit. And that was the Wurst decoupling, wideband uniform rate and smooth truncation. And as you may all know, Wurst is German and it means sausage. So yeah, the shape of the Wurst pulses, the chirp-like pulses, reminds of a sausage. And they have the big advantage that you have a constant amplitude here. So you do not have any outliers. So compared to the stud decoupling that I just showed, this adiabatic decoupling with a second and tangens hyperbolicus pulse shapes, this one has a very flat and equally distributed range of RF amplitudes and therefore better for the experimentalist. And with this, he could get even in one of the most extreme cases, a bandwidth here of 46 kilohertz and a Xi of 16.7. So it's really remarkable that you can do this. But of course, no one here in none of the sequences really looked at the sidebands. Well, I should point out there's now in the 2000s, so it started 2005 and the Bus sequence was published only in 2014, where there is a direct optimization of a single decoupling shape. So we do not optimize a 180-degree pulse anymore, but we simply optimize the whole sequence as such with its decoupling properties. And I think it's only now that this is computationally possible. And this Bus sequence here gives better decoupling than Wurst decoupling, for example, or here much better, of course, than the GARP4. And it gives better decoupling, no sidebands, I should point out. So here you see the coupled signal, and then for a certain offset range, it's being decoupled. And it's also shown here in the noise level what kind of sidebands you expect. So for the Wurst decoupling, which is highly periodic, you see here streaks of lines where the sidebands appear, while in the boost decoupling, if it's applied in a single scan even, you do not see any of these sidebands. And also in GARP, you see these sidebands, just to mention. But in Wurst, they are the worst because the Wurst pulses are relatively long. And what I told you in the beginning, it's simply that if you have a long pulse, then the sidebands increase. So what's the situation today? Well, the old pulse sequences, DIPSY2 is also a decoupling sequence, actually a very good one when you want to have very proper decoupling, but it has a small bandwidth. What's still used today a lot is GARP4 and Waltz 65, Waltz 64, both are used a lot when you have a carbon spectrum and you want to decouple the proton. Then this is sufficient and gives good results. However, if you want to decouple, when you want to have a proton spectrum and decouple the carbons, then you typically take the Wurst pulses, which are chirp pulses in the end. They're both equivalent. You take a robust phase cycle, so something like the P5 M4 that, well, I showed you. But then you, in addition, use tricks for artifact cancellations. And the one that seems to work really well is the bilevel decoupling. Just to show you a bit, so you have here this modulation of the signal because of a coupling. And now when you fully transform this signal, then you end up here with the sidebands. You know that from before. So these two harmonics. However, now you can add up scans. So the first one is the normal Wurst decoupling, where you have your adiabatic inversion pulse and you apply them many times. But then you acquire here, and the first pulse that you apply has a higher amplitude and has only half the length. So actually, here you have this periodicity, and now the periodicity starts halfway shifted because of this pulse here. And then you can apply this twice and 3 times, whatever, n times you can do this, but let's consider here 4 times. That's usually how it is applied. And what you then get is the red line, which is the conventional line. And then you take the first shifted sequence and then you get the blue evolution here. So it starts delayed, this periodicity. And that leads to a phase change in the sidebands. And in this case, to a 180-degree phase change, which means you take 2 scans, and if you add them up, you will subtract this sideband. And if you do it for these 4 scans, then even here, the subharmonic will be canceled out, while just taking half the sequence, shifted by half the pulse length, gives you only cancellation of the harmonic. So how does this look like when you do simulations and experiments? This is Wurst decoupling at 4.4 kilohertz, and this is the whole offset range of 40 kilohertz. You see over the whole bandwidth, you have very nice decoupling. This black signal here shows the decoupled maiden signal. And we assume 141 hertz J coupling. And then you see here the sidebands. They are on the order of up to 2%. And here what you see is this sideband plot that I showed you, but it's for several offset frequencies and all plotted on top of each other. Well, if you have the spectrum here, you look in this one side, you look along the stacked on the experiments. And that's what you see down here. And indeed, when you apply the two-step bilevel decoupling, you reduce quite a bit this artifact. And if you take the four-step, then even the subharmonic reduces to quite a low signal. So it works, and it's really something that you can implement on your spectrometer right away, and that I would recommend to use in most cases. However, we followed up, and we were very much interested in this bus concept. Steffen Glaser and Tom were involved, and many others. And yeah, we did this, but we did the optimization without periodicity, and we get sideband levels like the bilevel decoupling, but with a single scan and not by adding up 4 scans. So we can still improve this decoupling. Our question then is, can we reduce the power level that we need for decoupling? So we looked at it and we said, everything we showed so far was at 4.4 kilohertz, whatever. We are at the limit of the spectrometer. Can't we reduce this somehow? And so we were aiming for a sequence with a root mean square RF power of 2 kilohertz and a Xi of 20, meaning decouple 20 times more than the RF amplitude that we apply. So 2 kilohertz times 20 would be 40 kilohertz. Now, when we look here at adiabatic decoupling, then there are certain factors. The pulse length can increase, and if we have a longer pulse, then of course we can invert a larger bandwidth. On the other hand, with a larger pulse length, we can decrease the B1, the root mean square B1 energy. But on the other hand, we also show here in color code the adiabaticity factor. And the lower the adiabaticity factor goes, the worse are the pulse performances, meaning it's not really a 180-degree pulse anymore. You get all kinds of artifacts originating from this. At this moment, well, 4.4 is the quality factor of a constant adiabaticity Wurst pulse and also this bus sequences. And we're about here. They are 1.5 milliseconds long, but we need pretty much 4.4 kilohertz RF amplitude on average. And then you look into the Wurst decoupling at only 2 kilohertz, then for the same pulse length, you get a very low adiabaticity factor Q of only 0.9, and you introduce all kinds of artifacts from the pulse shape itself. Of course, you could simply go for a better quality of the pulse and make the pulse longer. But longer pulse means, again, stronger sidebands. So instead, we were aiming for pro code, which I will show in a minute. So this was, again, the performance of the 4.4 kilohertz pulse shape without bilevel decoupling and then introducing bilevel decoupling. And what you see here in red is the 1% level of sidebands. Now, when you apply it with 2 kilohertz, then you see what's going on. The pulse shape itself, even the best combination we found, has lots of sidebands. And even if you take the bilevel decoupling, the sidebands are significant. We are here talking more than 5% sidebands close to the signal. It's getting stronger and stronger. So we were looking for the Brocode advance, which means broadband cooperative decoupling. What we do is we optimize pulse shapes for the whole acquisition time, some 128 milliseconds typically, but not only one sequence, but actually the sequences for 4 consecutive scans. So we optimize the pulse shapes to compensate each other. We optimize them simultaneously. And so what you see here is the red one and the blue one, and you see where the blue one has a high signal, the red one is down, so they compensate each other in the end to get what you want to have is a smooth line here in the end. And you see it also in the sidebands, you see that some peaks will subtract each other. And so when we apply this, you see already here the sequence is just one scan, looks quite good. We have a noise level almost always below 1%, and that is at 2 kilohertz RF power. And when we apply 2 optimized scans, we get lower. And you see here, if we apply 4 of these cooperative decoupling scans, then the sidebands are really strongly reduced. And these are the simulations, and these are experimental values actually. So you can do it. Just a comparison. Here you see the bilevel decoupling with 4.4 kilohertz power, and there I think it's really fantastic what you can achieve. At 2 kilohertz, however, it's much lower quality, and then instead the Pro code at 2 kilohertz really gives quite nice data. Here the 0.5% level. We were looking, how does this really work in practice? And what we show here is a sample of imidacloprid, which is the worldwide most applied insecticide. It's from the company Bayer Crop Science. And that's the chemical formula. You see what it is used against. And when you acquire a spectrum of this, then you're interested, for example, to find a highly reactive but undesired educt shown here. And that typically comes up in the percentage range. So like 1%, sometimes a bit less, sometimes a bit more. But because it's chemically so similar, its peak comes in the range where there are C13 satellites and other things. So you would like to decouple, also to get rid of the satellites as a signal that you need to distinguish. But when you do this with Wurst decoupling, then you see here the sidebands and the signal. Would you say this is an impurity or not? Yeah, you cannot really distinguish, and down here even more so. And when we apply now the Pro code decoupling, you clearly see here the impurity, which is a 1% impurity. And this is at this low power. Why might it be useful to have this low power decoupling? Of course, it's better for the probe pad. Of course, it's better for the spectrometer. It's just more stable when you do not apply that much RF energy in the system. 4.4 kilohertz versus 2 kilohertz, that's a factor 2.2, and 2.2 squared. This is almost a factor of 5. So we have a factor of 5 less RF energy in the system when we apply this decoupling sequence, which is quite significant. Here's one example where this really has mattered. We have here a spectrum of Borneol and the H6N, H5X, and here H6, H5N. Here the signals overlap. And in the 1D, you cannot see which multiplet you have for simulating the spin system. We were interested in it, and of course you can separate these two signals by acquiring an HSQC. We did this, but then you want to have the multiplet, of course, nicely resolved to be able to simulate it. And if you use then standard 128 milliseconds acquisition time to the Fourier transform, then this is how the multiplet looks in the HSQC. And then you say, okay, I interpret the limit of the spectrometer quite positively. 200 milliseconds is about 256 milliseconds. So I acquire with 256 milliseconds. Well, at least I can see the 3 humps now separated. Still, this is not sufficient. But then you can go further when you do Pro code decoupling. I told you we have a factor of 5 less energy. So when you say 200 milliseconds is the limit with high power pulse decoupling, then it means we can do it a factor of 5 longer. We can now acquire over a second. Here we have 512 milliseconds, then the spectrum looks like this. And then even 1 second we can acquire, and you see the fine structures here of the multiplet starts to come up. And this we could nicely compare with simulations and indeed get out the coupling constants of this strongly coupled spin system. I hope I could convince you that heteronuclear decoupling has a lot of still improvements that we can do, and improving steadily, slowly but steadily. And you see now with this bilevel decoupling, I think you can really do a good job also in protein NMR, biomolecular NMR, as well as small molecule NMR. It would be good to use up-to-date sequences, and I assume soon we will make the ProCode decoupling also available. And I think this is another step in getting better and better spectra. With this, I would like to thank you all for your attention, and I hope you will enjoy this environment even further. Thank you. Any questions? Yeah. What is the algorithm for optimizing this? We use a so-called tracking algorithm based on optimal control theory. What does it do? You know, you have your FID. You start with maximum magnetization, and then you take one point, next point, next point, next point, next point, separated by 12 times. And what we kind of do is we look how well is the decoupling done in 1 12 time, or 2 12 times, 3 12 times, etc. We kind of in parallel compute all these 12 times, I mean, all the acquisition points at the same time. What is their transfer efficiency from all 12 points? We then calculate from the ideal, meaning perfect decoupling, back to the initial state. How is it behaving then? And then for each combination, we look at each 12 time, in which way can we define a gradient that improves the quality of the transfer, in this case, the not transfer, staying the same. If you do 128 milliseconds, I mean, we typically have a digitizations of 2 or 3 microseconds that we use there. You can calculate, this is a lot of pulses, and then a lot of steps in between just for one offset. We do it then for varying for several offsets and even consider B1 inhomogeneity. And so all this together gives a huge amount of calculations just for simulating these ones, and then we optimize it. And of course, such an optimization, even on a very good computer, is not finished in a day. Yeah, so that's what we're doing. But I mean, a lot of issues needed to be solved in this program, but we finally succeeded, as you see. And this is essentially an optimal control algorithm. And this tracking means it's not just a starting point and an end point, but it's a starting point and many endpoints that we all compare with each other. If power is not an issue, and usually it's not an issue with proton decoupling, then I indeed would continue using the Waltz or Dipsy. They are two very, very good sequences to decouple. Waltz has slightly larger bandwidth, so maybe Waltz is still indeed the choice, because they are relatively fast. I mean, it's short composite pulses, so there you get still, for a small bandwidth, maybe the best quality of decoupling. But it's only because the bandwidth is so small. And just would like to point out, like this, of course, everything is scaling linearly, also in the decoupling sequences. So we have now this ProCode decoupling with 2 kilohertz root mean square RF. And we can cover a bandwidth of 40 kilohertz. Now you think of fluorine. There you would like to decouple, I don't know how many 100 kilohertz. But with this sequence, we now, instead of 128 milliseconds and 2 kilohertz amplitude, we can apply it at 4.4 kilohertz amplitude, which then shrinks the length of something like 50-ish milliseconds. And of course, the bandwidth gets larger, which means we go then, instead of 40, we go to 88 kilohertz bandwidth. And also the size of the coupling that you can decouple, we optimized for 140 hertz, but now it's 2.2 times of it. So we're something of 300 hertz, which again, for fluorine, I think is important. So now you can even think of fluorine decoupling, broadband decoupling in this sense. Or if you, on the other hand, you say, I can live with also decouple smaller bandwidth, yeah, on some nucleus, let's say nitrogen or so, and there you have, instead of 140, you have 90 hertz. Then you can say, okay, 1.5 lower power. RF amplitude is reduced from 2 kilohertz by a factor of 1.5, so 1.33 kilohertz RF, which for nitrogen is really good. But then, of course, the bandwidth also shrinks. Yeah, but this you can do still, as with every pulse shape. Just with a normal pulse shape, you never look at the coupling. The coupling which you can decouple scales as well. Okay, so you say, I do now 1 second decoupling, and this would be a lot of RF energy in the probe pad. But what I said in the talk was, our decoupling sequence has only a factor 2.2 less in RF amplitude, which means the RF energy or the RF power is 2.2 squared, which is close to 5. So it's a factor of 5 lower in RF power. So I can apply it 5 times as long as I would be able to apply the hard pulse power. I mean, the conventional GARP decoupling or whatever you do. And so instead of 200 milliseconds, I would be able to do it for 1.2 seconds and apply the same overall RF energy. So when you can do on your probe pad with a conventional sequence 200 milliseconds, then with this sequence, you can do 1.2 seconds with the same power, because power is the limiting factor.